The bounce of a ball. That is not very bouncy. The sound of a bouncy ball bouncing has sort of interested me for quite a while. The idea of the process of it losing momentum, and as it moves momentum, every single bounce gets quicker and quicker and closer together. It makes quite an interesting sequence of triggers. And this video today is about simulating that effect. Be it the very old-fashioned way, or doing it with electronics, much like this thing that's on the wall right here that we're going to look at building a little bit later in this video. This is a miniature analog computer that I put together out of spare parts to show the bouncing ball being simulated using analog electronics. This computer is wired up a little bit quick, so it's sort of like bouncing a ball with double gravity or something. It has controls over the gravity, the dampening and the elasticity, and putting all these together you can sort of make a rudimentary example of a bouncing ball. Have a look over here. I mean, that's a very bouncy ball. So I've been into this bouncy ball idea for quite a while. I built this module about 5 or 6 years ago, and it was my rendition of quite a dodgy bouncy ball. The code has long since gone, and this Arduino is sadly not working, so I don't know what to do with this one. It's bust. But as you can see, it's got a bouncy ball drawing on the front. The idea is you set the parameters, you wire this up to a certain voltage input source of like a filter or a VCA or something like that. You press go, and it goes boop, 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 and pretends to be a bouncing ball. And when I was surfing the World Wide Web, I came across a chip by Electric Druid that actually acts as a bouncy ball simulator. It was called the One Shot. When I saw this chip, it rekindled my interest in bouncing balls and stuff. So I built a module around it called the bounce, 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 bounce. You know, like bounce, 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 bounce. So this is a bouncing ball simulator module in Cosmo format. The PCB panel and chipset is available for this over on my shop. So if you want to build this, then by all means do so. This actually goes above and beyond the original bouncing ball simulator because it's got extra waveforms. Anyway, let's go and have a closer look at this. Oh, and by the way, at the end of this video, there's a bonus round of putting one of these together. So this is the bouncing ball simulator in question. I'm just going to quickly plug in this over here, which is a filter that has got the resonance on max, so it's making a clean sine wave. And this filter is wired up to the input of this VCA. I'm going to wire up the bouncy ball simulator to the CV input of the VCA, and now we should be able to get, if I get this up, there we go. It's got a bunch of different waveforms of how you want your bounce to go bouncy bouncy. It's got how quick you want that bounce to bounce, how many repeats of bouncy repeats you want, and then how many delays between the bounces. If I send in an oscillator into this filter, and also send the CV output of the bouncy ball modulator into the CV input of the filter, it makes a funky effect because every single bounce goes down in amplitude. Trigger the bouncy ball with something else like an LFO over here. But you can also send the CV out into the oscillator's input as well. Screw it, why not? The bouncing ball module also has control voltage over all the knobs, so you can make it do some pretty random bounces here and there. And this is a video I shot. And this is the video I shot of the prototype when it was doing a load of random bounces. After I finished that module, I still wanted to tackle the bouncing ball simulator in an analog computer kind of realm. It all started about 50 years ago when Telefunken published this document. It's called Ball in a Box. It outlines basically how to simulate a bouncing ball bouncing in a box on your Telefunken analog computer, because everybody in the 60s apparently had one of these in their living room. So this Telefunken document is Ball in the Box. It's a simulator that simulates a ball bouncing in a box, and it sort of tells you what to do with your Telefunken analog computer, because obviously everybody has a Telefunken analog computer. Well, a shout out to Niels E La 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 and Marknet. Marknet actually translated this document over on my Patreon. Here it is. There's a link below to everything. So yeah, this is the translated version. It talks about the mechanics of the bouncing ball, including the initial speed and how it is dampened and changed by the elasticity of the ball, the gravity, damping effect of the air, this, that and the other. It's pretty cool. So this simulation actually involves 3 separate computations. It involves this one, which is the y-axis being up and down. It involves this one being the x-axis, which is, and there's also a computation to make a ball on the screen. So the synth module I was talking about previously only does the y-axis. That's where it bounces up and down and slowly loses momentum all in the same line. It's like dropping a ball, it just bounces up and down by itself. The x-axis is imagining if you're throwing the ball a bit, and that is this computation. So this computation goes into the y-axis of the oscilloscope, that's the up and down of it, and then this one goes into the left and right input. And then the ball, these 2 separate signals, this being y and this being x, are added to these 2 separate signals. So there's 2 mixers. This mixes the signal from this computation and this element of the computation here. So basically what that does is it sort of, as this goes up and down, it goes wiggle, 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 because this is being sent in trying to make a ball. But it doesn't look like a ball until you get this as well. So it goes wiggle, 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 wiggle. So there's 3 separate computations going on here in this document. However, we're not going to be using this one or this one because I just don't feel it's that important. And right now I am barely grasping onto the theory of analog computers, and the y-axis is fun enough on its own. So I think the y-axis is good enough for this video and a demonstration machine for the museum. Happy days. Here's another good piece of documentation. This is also linked below. It's by Dr. Ayers. I don't know how to pronounce it. And over here, if you go over to this page, you will see that this is a nice, happy schematic. And this schematic right here is basically a tiny little analog computer that is made to calculate the y-axis. This is the original drawing from the Telefunken document of the y-axis. This one involves an integrator, and then these 2 actually set the bottom and the top of the box. But we're not bouncing in a box, we're bouncing on our own. If you've ever looked at an analog synthesizer schematic, you will notice that there's actually quite a lot of crossover between this schematic and, you know, any old analog synthesizer thing. That's because an analog synthesizer is basically an analog computer in a party frock. They share a lot of things in common. For instance, integrators in analog computers, you'd find these things a lot in things like envelope generators and anything that needs to do anything over time. Summers and mixers are basically just things that mix voltages together in modular synthesizers, and things like rectifiers and stuff, which are just analog waveforms and, you know, fold them in on itself like wave folders and this, that and the other. I'm personally still getting to grips with analog computers, so I'm very much brushing over the absolute detail in this video, and hopefully over time I'll get to know a lot more. There's a really good book by Bernd Ullman, who Hainbach actually did a Q&A live stream on. The links below. The confusion I have around analog computers right now remind me of the confusion that I had around modular synths before, so hopefully with a bit of persistence I'll get my head around all of this stuff. What surprised me initially is the simplicity of the circuit. What is required are 2 integrators to calculate the velocity and the acceleration, and then it goes back on itself via a rectifier, which is just a diode, and I still haven't managed to get this to work, but I found a rather sketchy solution regardless. I went on to check out Bernd Ullman's pieces on the bouncing ball, which is actually even covered in his book, and I haven't got to that part of the book yet because it's pretty heavy on the old brain, but he basically touches on the same situation that is talked about in the Telefunken document as well as this document, and it also comes out to a very similar looking schematic, albeit it's laid out in a different way. This right here is the first integrator, and this actually goes in to the second integrator. The difference between these integrators and the integrators that I've shown you before is these are bypassable. There's actually switches right here that means you can turn on and off the integrators to charge them up, and these are the things that are needed to get the ball bouncing. So after a little bit of trial and error, this is the schematic. So before we dig in, to get it out of the way, if you don't know what these schematics schematic symbols are, well, this right here actually is about the same size, is a resistor. Capacitor looks like this. Ooh. Switch looks like this. You can notice, you see this line right there that can bounce between these 2 points. So this is the common one, and it goes click, click, click. And these triangles are called operational amplifiers. Think of operational amplifiers like Swiss Army knives in analog electronics. They could do practically anything you chuck at them. Where are these symbols? Well, there are actually different packages of these symbols. For instance, very common used ones in synthesizer circuits are the TLO71, which is a single op amp inside a chip. You could get a TLO72, which is basically 2 of them in a single chip, or you can get a TLO74, which is 4 of them in a single chip. Also, you will notice that this one says TLO74 over the top of it, and also the leg numbers of the chip to make it a little bit simpler, and most schematics have these on them. Worth mentioning that these chips also require a power supply, and that is what is usually denoted by something like this. Pin 4 of this, you plug into plus 12 volts of the synthesizer power supply, and pin 11 of this, you plug into the minus 12 volts of the synthesizer power supply, and boom, you've got power. So after those pleasantries, what do we have here? Well, you'll notice it actually looks relatively similar-ish to the other schematics. So we have the first integrator, which goes into the second integrator. It's inverted and then it goes back on itself again. It's that easy. And then there's these funky things, which are potentiometers. These are the ones that have got the twisty knobs on them. If you look, there's a 1, a 2 that is slightly obscured. I just realized, I'm sorry, and a 3. That corresponds to the 3 legs on the potentiometer. And you'll notice it looks very similar to a resistor symbol with an arrow in the middle. That's because this is a variable resistor. This whole circuit was giving me a little bit of a problem, and you never know, somebody might comment a very obvious fix for this that I just completely overlooked. I've tried rectifiers everywhere and it just wasn't quite working. What the problem was is, imagine this is the floor. I was bouncing the ball on Mars. Basically what it was doing was it was going like this. It was going through the floor, back up again, through the floor. If you've ever seen a bouncy ball bounce through the floor and come back up again, then you would know what I mean. I was reasonably confused and flabbergasted. That's where I use this circuit right here. I wired the output of the other circuit into this. This is called a dual wave rectifier. And in synthesizer terms, it's the kind of principles of a wave folder. What this does is it takes your kind of bipolar signal. Imagine this is the signal that it receives. What it does is it's sort of like an electronic calzone. Imagine this is a pizza. It takes all of these voltages under the floor and says, hey, why don't you come up here? I'll fold you over. And it basically folds them and turns them on top of themselves, and it comes out like this. And that looks a little bit more like a bouncing ball. This op amp is set to invert the signal, but then also it gets rectified. So it sort of deletes itself and then pops itself back in backwards. I'm sort of drawing Viennettas. This absolute monstrosity right here is the breadboard version. I know a lot of YouTubers have very clean and neat breadboard layouts, but I decided to keep it messy. It's sort of like going without makeup on a magazine front. You know, this is how I am. This is how I live. You'll notice these big chunky capacitors. That's where the integrators are based. And there's the 3 knobs that were controlling the elasticity, the gravity, and the dampening. And yeah, this whole circuit right here is the bouncing ball circuit. In the version I'm about to build for the museum, there's going to be 4 relays that control the switches that were in the schematic. Basically, when these switches are down, it's the initial position of the ball. And when you flip these up, it turns the integrators on and makes the analog computer computate. 3, 2, 1, and lift off. Oh yeah. By the way, there are 3 states that analog computers do their thing. There's initial value, there's compute, and there's halt. And what halt does is it sort of pauses it so you can sort of take a reading. Watch. So if I do it halfway, if I stop it halfway through, oh look, and then it carry it on. What you do there is keep the integrators integrating, but stop it from receiving any more information. However, you'll notice there's a little bit of a problem here. There is actually no sound. So the problem is when you listen to this waveform, it doesn't sound like much because it just makes the speaker go backwards and forwards rather slowly. It's not really an audible sound. What we need to do is we need to find a way of sending a blip to the speaker every time the voltage hits nearly 0. Well, we use our good old friend, the op amp, the analog Swiss Army knife, which has an output, an inverting input, and a non-inverting input. And it has an amazing amount of uses. And we're going to use right now is called a comparator. What that means is it turns on at a certain point. What we do is we plug the bouncing ball into the inverting input. That means that this op amp is listening to the voltages that are going like this. And we're going to use the non-inverting input as a reference point. We're going to send a voltage into here and say, hey, every time this bouncing ball goes below that certain voltage, we want you to turn on and make the speaker go boom. And how we do that is we use a couple of resistors. One resistor, which is about 330k, is connected to 12 volts. And then there's another resistor that is 1k, and this is connected to ground. And because this resistor is relatively small and this resistor is relatively large, the voltage reference is going to be extremely low, and it's actually very close to zero. So every time this bouncing ball gets below this voltage reference, well, it's going to turn this on, and that's going to make a tiny little blip. It's not perfect for a number of reasons, but it'll do just fine for us right now. I've added this rather lo-fi speaker circuit design into the schematic. It's not perfect, it's not very good, but it's there anyway. Anyway, let's get building. Okay, first things first, we're going to use this skanky old enclosure that I've had sitting around and this random old speaker. I'm going to cut some holes first so that you can actually hear the speaker move in the air in the place. And then we're going to use this strip board and this arcade button. And then we're going to make the strip board layout. What I do is I usually just kind of follow the schematic and make it up as I go. And then carefully, whilst I'm checking, just putting all the dots together and then crossing out the bits I put in and just keep on going like that. These are the relays that I'm going to use. I downloaded and printed out the data sheet so I knew exactly which pin did what, and then I basically put down some sockets for them and just copied where the pins go and just kept on soldering and added them to the strip board layout. So they are now the switches. So instead of there being switches like in the breadboard, there's relays. And I use this weird Medusa looking thing that I just got. It's amazing. Search up helping hand. Yeah, it makes it very easy to solder potentiometers in place. And then you put the potentiometers, just kind of figure it out. Just be very careful. I would thoroughly recommend you try this method of making strip boards. It means that you're able to make strip boards out of anything. Instead of copying layouts and confusing strip board layouts, you go straight from the schematic. It means that you're learning something at the same time as building it. And then look, it works! It works! So as you can see, the one that I made up looks a little bit dirty, but it's functional. I've made sure that every single solder joint is nice and neat and stuff, so it actually works. From the back, you could see I did make some wires going to other bits and stuff, but we'll look over that. Just try making it up. Just give it a go. And then connect it all together, putting it all in place, and it should all be going to plan. Use standoffs to put on the strip boards, and boom! I managed to get this working first time. Yeah, sometimes you're just pretty lucky. And yeah, finish it off with a lovely doodle. It is pretty ropey looking, but it has got an element of like 1970s homemade-ness, except for the arcade button, of course. It's pretty snazzy, actually. And then I used this frequency central power supply that I had sitting around. I put it inside the box. I made this all from stuff I had lying around because, you know, it's cheap and quick. And then I put it together and it looks lovely. Oh, look, it works! Right, so it's now done, and I'm quite pleased with it. It's not the best ever rendition of the bouncing ball simulation. I could have fine-tuned it till the cows came home, but it's enough for a bit of fun. Like, you could get it to go forever. Oh. Or you can make it stop reasonably quickly. Like, turn the gravity down a bit. Turn the dampening up. I think this will get played quite a bit because it is quite addictive. That is so cool. So I've put this bit of conduit and wood together, and this should cover up the cables from little fingers. Not bad at all. With this project, I merely dipped my toes, so to speak, into the analog computer realm. The next step with this is I'm going to build the whole bouncing ball in a box simulator and just give that a go, and hopefully after that I'll have a little bit more idea of what's going on with analog computers, and I can carry it on further because it is truly interesting, and it's just like an untapped thing for me, and it's fascinating. I've included the links and all the reading material below of everything that's influenced me and kind of taught me everything in this video. I've been talking about the progression of this project over on my Patreon for the last few weeks, along with a load of other projects that I'm working on at the minute to try and get done. There's a couple of big ones as well, and needless to say, the Patreon helps to support all of these builds and the museum that hopefully will open one day. There's also a bunch of sound files that I recorded whilst I was doing this video, so they're available for download over on my Patreon as well. So if you want to think about supporting this stuff, then please go and check it out. Anyway, I've been Look Mum No Computer. If you like bouncy balls, don't forget to subscribe, and yeah, don't be scared to try it. Oh, and by the way, this is a bonus round of building a bounce. Anyway, take care. Okay, this is everything you're gonna need. All of the resistors, the PCB chip panel set, the jacks, the potentiometers, and everything. Look at my hand. I managed to drop my phone in a hedge, so I've got I had to pull it out. I just got loads of it. Anyway, you start with the resistors, and you just keep on soldering those, and then you put the diodes in. These need to be the right way round, and there's a list that just check on the internet, and it's very obvious. And then you keep on going up. The bigger the component, the later you leave it, and then you pop in the connectors and stuff, because they are rather high and it makes it easier. And then you put in the potentiometers into the PCB, but you don't solder them, because if you solder them they can go in wonky. And then you tighten it up, pop the LEDs, making sure everything's in place, and then solder everything down. It is a little bit tricky. This one's actually quite tight, so it requires a little bit of delicate care and attention. Do exactly the same with the jacks. Put them in first and then solder them, making sure everything is straight and flush with the panel. Then pop in all of the pins and all the way round, and then you're nearly pretty much done. You put in the knobs and stuff, and hopefully, fingers crossed, you've got yourself a working big mama of a lovely bouncy. Anyway, I'll see you next time. Have a lovely time. Don't forget to subscribe and all that jizz jazz, and toodly doodly doodly doo.